Welcome to module 28. In this module, we will discuss some special discrete distributions of practical importance. So first, let us consider a general setup for discrete random variables. So suppose x is a discrete random variable with support as x and distribution function fx, and suppose small fx is the probability mass function of x. Then we know that mu, which is expected value of x, is given by summation x belonging to Sx x fxx. Sigma square, which is variance of x, is given by expected value of x minus mu whole square, which is same as summation x belonging to Sx x minus mu whole square fxx. In general, for any function h, the expected value of hx is given by I sum hx along with fxx over the support of x, provided this sum is finite. We also know that the moment genetic function is given by mxt, which is expected value of e to power tx, which is summation x belonging to Sx e to power tx fxx, wherever this sum is finite. So for whatever values of t, this sum is finite. So this is a general setup for discrete random variable. So first distribution which I study is the Bernoulli distribution, then a general form of Bernoulli distribution which is called the binomial distribution. First, let me define what do you mean by a Bernoulli experiment. A Bernoulli experiment is a random experiment that results in just two possible outcomes, say success S and failure F. So suppose my random experiment is such that it results in two possible outcomes. One of them is taken as a success and one of them is taken as a failure. If that is the situation, then my sample space is S comma F. My event space is phi, omega, singleton S and singleton F. Now suppose my random experiment is such that probability of success is P, then of course probability of failure, which is P of F, would be 1 minus P, which is Q, because there are just two outcomes, S or F, where P is between 0 to 1. Now I define a random variable x from omega to r, which is number of successes I get in a single trial. In a single trial, number of successes would be 0 or 1. So it would be 1 if I obtain a success. This would be 0 if I obtain a failure. So these are number of successes in a single trial. Now for this random variable, I know my support Sx is 0, 1. What is the probability mass function of x? Fxx, which is probability x equal to x. If x is 0, that means I obtain a failure. Probability of failure is q, which is 1 minus p. If x is 1, that means I obtain a success and probability of success is p. So my probability mass function is s. Now this is called a Bernoulli distribution. Note that this Bernoulli distribution has one parameter, which is p. Q is nothing but 1 minus p. So this is can be written as, because if x is 0, this quantity would be nothing but q, which is the probability of failure. If x is 1, this would be nothing but q to power 1 minus 1, 0, q to power 0 is 1, so p, so which is the probability of success. So in a closed form, this can be written as p to power x, q to power 1 minus x. Now this is nothing but a Bernoulli distribution with success probability p, which is anything between 0 to 1. Now let us consider a generalization of a Bernoulli distribution. So now suppose I am considering a sequence of n independent Bernoulli trials. So that means my random experiment has been repeated n times, and each time I either get a success S or a failure F. And this probability of success is the same from trial to trial, and my trials are also independent. And suppose x is number of successes in n Bernoulli trials. Note that if n was 1, I have a usual Bernoulli distribution. Now I am considering the n Bernoulli trials which are independent in nature. Since I am talking about number of successes in n Bernoulli trials, my support would be 0, 1, 2, and so on. What would be a probability mass function of x? Fxx, which is probability x equal to x. So that means I obtain x successes. So that means I obtain S in x trials and I obtain F in n minus x trials. My trials are 1, 2, 3 n. And what I want is, out of these n trials, I get s in x trials. Now, this s in x trials can occur in any of the x trials out of these n trials. So, this can happen if I obtain a sequence of failures and success in the following form: failure SS F F S S F S. I will have to look at all such configurations such that I get x s and n minus x f. Because the trials are independent, so this is same as probability of obtaining failure in the first trial, which is q, then probability of obtaining success in the second trial. Since trials are independent, this would be q multiplied by p. Then success in the third trial, again trial are independent, so probability multiplied by probability of p, probability of success, which is p, then failure, which is q, then q, then p, p, then q. Since there are s successes, I will get p x times, so I will get p to power x, 1 minus p to power n minus x. And I have to look at all such possible configurations. Each of these configurations gives rise to probability px 1 minus p to power n minus x. And how many such configurations would be possible? That would be identifying in what trials I am getting s. And I want x s, so that is same as choosing x positions out of n positions for the s, that is having n. So, there will be n choose x terms of this type, p to power x 1 minus p to power n minus x. That will give me s in x trials and f in n minus x trials. So, f x x is n choose x p to power x 1 minus p to power x minus n minus x if x is from 0 to n and 0 otherwise. So, this is the distribution of number of successes in n independent Bernoulli trials, and this is called the binomial distribution, and of course, it has two parameters, n and p. So, this is a binomial distribution with parameters n, which is number of trials, and p, which is the probability of success in each trial. And we write down this as x follows binomial distribution with parameters n and p. Here n is any natural number, fixed natural number, and p is belonging to 0 to 1, and these are the two parameters. So, binomial distribution in a sense is a family of distributions. For each n and p, I get a different binomial distribution. Certainly, for n is equal to 1, I have a Bernoulli distribution. So, a binomial 1p distribution is a Bernoulli distribution with success probability p. Now, let us try to find out the movement generating function of binomial distribution. That will give me the all movements of binomial distribution. So, suppose x has binomial np, where n is positive integer, p is between 0 to 1, and q is 1 minus p. So, movement generating function mxt is expected value of e to power tx. That means, I have to sum e to power tx in the support x equal to 0 to n along with the probability mass function, which is n choose x, p to power x, q to power n minus x. Now, e to power t, p can be combined. So, that becomes p t to power x, n choose x was anyway here, and then q to power n minus x. Now, if you look at this whole quantity, this is nothing but expansion of q plus p t to power n, and this is finite for every t belonging to R, because this is anyway is a finite sum. So, my moment generating function of binomial distribution is q plus p t to power n. Now, once I have a moment generating function, finding moments is straightforward. So, I look at the first derivative of mxt. So, my moment generating function, note that is q plus p t to power n. So, I take the first derivative of mxt, which is n p t q plus p t to power n minus 1 t belonging to R. I take the second derivative. So, that means, I take differentiate mx1 t, which turns out to be n p t q p plus p t to power n minus 1 plus n into n minus 1 p square e to power 2 t q plus p t to power n minus 2. So, if I have to get the mean of the distribution, mu is equal to x of x, I put t is equal to 0 in the first derivative of the moment generating function. So, mx1 0. If you put mx1 0, t is equal to 0 gives me q plus p to power n minus 1, but q plus p is 1. So, that gives me 1. E to power 0 is 1. So, the mean is np. X of x square That means I put t is equal to 0 in the second derivative of movement generating function. T is equal to 0, this gives me q plus p, which is 1. E to power t at t is equal to 0 is 1, so this gives me np. Let us look at the second term, n into n minus 1, p square. E to power 0 is 1, so 1, q plus p to power n minus 2, that is again 1, so this is 1. Now I have to get sigma square, which is variance of x. We know that variance of x is nothing but expected value of x square minus expected value of x whole square, which is same as this quantity minus square of this quantity, which is nothing but np into 1 minus p. So I get mean as np and variance as npq. Now note that q is 1 minus p is always between 0 to 1. So q is always less than 1. So that means my variance is always smaller than the mean. So this quantity is always smaller than np. So that is why you get variance is smaller than the mean. So for the binomial distribution, the mean is always larger than the variance, strictly larger than the variance. Now let us do this result, which is about the reproductive property of binomial distribution. This says let x1, x2, xk be independent random variables. Suppose xi has binomial nip. So they are independent. Probability of success is same for each xi, but number of trials are different, which are ni. And suppose x1, x2, xk are independent. Then y is equal to summation xi again has a binomial distribution with number of trials as summation I is equal to 1 to k ni and probability of success as p. Let us try to prove this. Myt is same as expected value of e to power t summation xi, and I know that movement generating function of sum of independent random variables is same as the product of individual movement generating functions. So this turns out to be the product of movement generating function of xi's. But xi is binomial nip. Its movement generating function would be nothing but q plus p t to power ni. Note that this p was same for each of the xi's, so that is why I don't get qi, rather I get q. Now these exponents then get added, so this becomes q plus p t to power ni. But this is same as the mgf of binomial summation I is equal to 1 to k ni p. So this shows that movement generating function of y is same as the movement generating function of binomial summation I is equal to 1 to k ni p. So by the uniqueness property of movement generating function, y has binomial summation I is equal to 1 to k ni. So binomial distribution has reproductive property if you are having independent binomial distributions. Now this intuitively also looks okay, because what I am saying is x1, x2, xk. So suppose there is a random experiment which results in two possible outcomes, success or failure. X1 is, let us say, a person number 1 performs random experiment n1 times, and he gets xi successes. Then there is a second person who performs independently random experiment n2 times. Probability of success is same. Then there is a kth person, he independently performs random experiment, and the probability of success again is same, p for them. Then y is summation I is equal to 1 to k xi is nothing but number of successes obtained by all the persons together, k persons together. Now here these persons are performing a random experiment independently. So it looks like the distribution of y would be same as if the random experiment has been performed summation I is equal to 1 to k ni times independently with probability of success as same, which is p in each trial. So intuitively also this result is very appealing. Now let us come to another distribution, which is a negative binomial distribution. So suppose you have a sequence of independent Bernoulli trials with probability of success in each trial as p, which is same from trial to trial. So probability of success does not change from trial to trial. Let r belonging to n be a fixed positive integer. So your random experiment has been performed n times. And suppose y is the number of failures preceding the rth success. That is my random variable. Or in other words, y plus 1 is the number of trials required to get the Rh success, because y is the number of fellows preceding the Rh success. That means y plus 1, in the y plus 1th trial I got the Rh success. So, y plus 1 is the number of trials required to get the Rh success. So, since number of fellows preceding the Rh success could be 0, 1, 2 or so on, so my support of y is 0, 1, 2 and so on. Now, let us look at what happens for small y belonging to Sy. Let us try to see what is the probability mass function Fyy, which is probability y is equal to y, which means that there are small y fellows preceding the Rh success. So, what it means is total number of trials, that means is R plus y, and R plus yth trial is a success, and in R plus y minus 1 trials before this success I have got only y fellows. So, that means or R minus 1 successes, y fellows or R minus 1 successes. This same as saying that probability of R minus 1 successes in y plus R minus 1 trials, and y plus Rth trial is a success. Since trials are independent, probability of obtaining success in R plus 1th trial is P. Multiplied by probability of getting R minus 1 successes in y plus R minus 1 trials. You have a sequence of Bernoulli trials, and I am saying you get R minus 1 successes in y plus R minus 1 Bernoulli trials. So, that is given by binomial distribution. So, that would be given by y plus R minus 1, choose R minus 1, p to power R minus 1, 1 minus p to power y plus R minus 1 minus R minus 1, which is y. So, if you simplify this, this turns out to be y plus R minus 1, choose R minus 1, p to power R, 1 minus p to power y. So, I have got the probability mass function of y, which is number of fellows preceding the Rh success. So, the probability mass function of y is given by this quantity, which is y plus R minus 1, choose R minus 1, p to power R, q to power y, if y is from 0, 1 to so on, and 0 otherwise. Here q is as usual 1 minus p. Now, this is a negative binomial distribution. It has two parameters, R and the probability of success in each trial, and we write down this as x follows negative binomial with parameters R and p. Just to see whether this is a proper probability mass function or not, clearly Fyy is greater than or equal to 0, because p is greater than 0, 1 q is greater than 0, this quantity would be greater than or equal to 0. Let us look at summation y belonging to Sy Fyy. My Sy is 0, 1, 2, so on. So, that means sum y is equal to 0 to infinity. There is no y in p to power r, so p to power r goes outside, and you are summing then y plus r minus 1, choose r minus 1 along with qy. This is p to power r. Let us try to see what is this. Y is equal to 0 gives me r minus 1, choose r minus 1, which is q to power 0 is 1. Then y is equal to 1, which is r choose r minus 1. R choose r minus 1 is r, q to power y 1, which is q. Similarly, then y is equal to 2. Y is equal to 2 gives me r plus 1, choose r minus 1, which is nothing but r into r plus 1 by factorial 2. Y is equal to 2 q square. Then the third term, fourth term, r plus 1, r plus 2 factorial 3 q cube, and so on, which is same as p to power r. Now, note that this quantity is nothing but expansion of 1 minus q to power minus r, because q is between 0 to 1. So, this turns out to be 1. So, it is a proper probability mass function. Let us look at the movement density function of y. myt is expected of e to power ty. So, you sum e to power ty in support, which is 0 to infinity, along with probability mass function, which is this quantity y plus r minus 1, choose r minus 1, p to power r, q to power y. P to power r goes outside, summation y is equal to 0 to infinity, y plus r minus 1, r minus 1, q e t to power y. Note that when e to power t was not there, this was nothing but expansion of 1 minus q to power minus r. So, now it would be expansion of 1 minus q e t to power minus r. The only thing we have to make sure is this quantity is less than 1 for this series to be convergent. So, I want q e t should be less than 1, or e t is less than 1 by q. So, that means t should be less than minus log q. So, for this series to be convergent, t is less than minus log q. Minus log q is positive. So, this is 0, minus log q is over here. So, my movement density function exists all over in this range. So, in particular, my movement generating function exists in a neighborhood of 0. So, all movements exist and one can get the movements from movement generating function. So, let us try to see what is psi y t, which is log of m by t. Log of m by t is nothing but r log p minus r log 1 minus q e to power t. So, I differentiate psi by t, which is log of m by t, and then I put t is equal to 0, that will give me mean. If I differentiate it twice and put t is equal to 0, that will give me the variance. So, psi y1 t is this quantity for t less than minus log q. I differentiate it once more to get psi y2 t, which is r q comes outside, and I differentiate then e to power t upon 1 minus q e to power t, which is 1 minus q e t square, 1 minus q e t differential of e to power t, then minus e to power t differential of this, which is minus q e t, minus minus becomes plus, so it becomes q e to power 2t. So, my mu, which is expected y, is nothing but psi y1 0. Psi y1 0 is nothing but e to power 0 is 1. So, r q divided by 1 minus q e to power 0 is 1. So, r q upon 1 minus q, which is nothing but r q by p. Let us look at sigma square, which is variance of y. Variance of y is nothing but psi y2 0, because psi y t was log of m by t. So, r q is outside, t is equal to 0, 1 minus q. Here t is equal to 0 e to power t, t will give q. So, 1 minus q plus q, which is 1. So, which becomes r q divided by 1 minus q e to power 0 is 1. So, 1 minus q whole square, which is p square. So, r q by p square. So, here you can, since p is between 0 and 1, r q by p square is always greater than r q by p. So, here what you observe is variance is always bigger than mean, or mean is smaller than variance. So, for the binomial distribution, we saw that variance was smaller than mean, but for negative binomial distribution, mean is smaller than the variance.